Okay, so here is another example, an oblique example for class 11. I think this is going to be my last example for right here. So we have these two discs, and they have different sizes this time. Boy, this thing is really kind of shaky right now. And initial velocities are shown. So 15 meters per second and 8 meters per second. So they're coming towards each other, and but not directly at each other. And they have masses of 4 kilograms. So this one is bigger and faster. And this one's 2 kilograms, he's slower. And so we have a coefficient of restitution of 0.8. So this is a pretty good problem because it gets rid of a lot of the simplifications, right? So it's like almost close as to a generic problem as you can get. So let's draw this thing out here in our initial, our impact, and our final. Or we could say it was an impulse, right? Whatever you want to call that right there. And we're going to draw in our normal thing right here, and I decided that the normal direction was going to be here and the tangentials right there, right? So we're going to take that impact kaplui right in here, and it's going to be equal to, that's not really the same angle, is it? It's actually pretty close when I look at it from that point of view. A little parallax error going on here. And then here is going to be the final right here. So we draw this right here. We say this is M, and what's that, B? VB1. This one right here, I'm going to draw it as MA VA1 normal. And let's see, because we're going to break this thing apart, right? So this one has a component in that direction and has a component in that direction. So it's going to actually, so we actually have, I like to draw them at the center right here. A little bit more. They are particles, so they don't really have a location exactly. But MA VA1 tangential. So when we get this one right here, we know that that's going to be MA VA2 tangential, and I'm gonna predict it's gonna keep going. It's so large and got so much. I'll say this MA VA2 in the normal direction. This one, I'm predicting this one's going backwards. Hopefully we won't get any. We won't have any problems with the signs. Like we make it a negative number, and we go, oh, we made a bad prediction. So a lot of times choosing in the positive direction will make anything. So this is actually the positive direction that I've kind of done right there. So, all right. So one thing I want to break this down into normal and tangential. So I'll say that the A1 normal right here is the 15 times, let's see, that's going to be, I always mess around when I have this crazy 3, 4, 5 thing. This always bothers me. Should I use the 3 or well, use the 3 this time. I worked it out. You can too. And then the VA1 tangential right here is just the 15 times the 4/5, or 12 meters per second right there. Okay. And you can mess around with the triangle and figure that out too. So in the tangential direction, we know that it's this one. I'm not even going to bother to write it down. That this one in tangential direction is also equal to A2 in the tangential direction. So we're good there. So now in the normal direction, we say this one needs to be minus right here. So I change where I put the minus. I'm gonna put it inside here. So this guy is 2 kilograms. He's 4 kilograms. He's 2 kilograms, and he's traveling in the negative n direction as we've defined it at 8 right here. And then this guy right here is in the positive direction, and he's 4 kilograms, and he's traveling at the 9. Right? And it's going to equal, now we're assuming this is positive, so he's 2 times VB2, right? I didn't even bother with the normal because I know he's going completely in the normal direction. And then plus 4 times VA2 normal, right? So we don't know this guy right here. So we could write out the equation. If I manipulate this equation right here a little bit, I can have VB2, I'm going to divide by 2 all the way through, is going plus 2 VA2 normal is going to equal 2. It's going to end up being 10, because this, right, when you add these two together, is 20. We're dividing out by 2. So this is going to be our equation 1 that we have right here. We apply our coefficient of restitution to this thing, and we say that E, and I'll write out the equation, is VB2N minus VA2N divided by VA1N minus VB1N. So we had to be careful with our signs right here. Here's VB2, we decided, right? We're just going to call it that, and VA2N right here. So this one is traveling at 9, right? That's the part right here. Minus, but you got to be careful with that minus right there. That has to be minus, right? So these things do have signs and direction, and that's going to be equal to the 0.8. So when we write out an equation for this, we could say that VB2 minus VA2N is going to equal to 13.6 is what we find. Is that true? Yeah, because that's going to be 17 times 0.8. So this is going to be our second equation. So if you solve for 1 and 2, right in here, we have simultaneous equations, right? Or we can just stick them back in. Either way that we want to try to do it to manipulate this, I found that VA2N was negative 1.20. Ooh, look at that. So it does bounce off. This does bounce backwards, right? Counterintuitive. But maybe it's because this only had 9 in that direction. So it does bounce off and go back upwards down that way. And then we also found that VB2 was going to be positive, which we were pretty sure of, and it's going to be 12.40. So that's pretty impressive that it has changed that direction right here. So when we go to write out the answer to this, we have to be a little careful with our directions. First off, we found out that VA2 is going to be the square root of 1.2 squared plus our 12 squared. So we're going to get really close to 12, right? It actually turns out to be 12.06 meters per second, because this one's so much bigger than that one. For the angle now, here's what we have to be careful with. This is going to be A2 for the thing. We take the inverse tangent, and that's rise over run. And in terms of our rise, what we're going to consider rise maybe is going to be this component, right? The tangential component. Was I correct there? Yeah, it's going to be 12 over 1.2, and I end up getting 84.29 degrees, but that's with respect to this axis right here. So if I were to find out what this angle is right here, it's 53.13 degrees. So what we have said, though, actually, is that the angle that we've just measured right here was our 84.29 degrees. So if you take a look at this right here, the actual angle is this one plus this one, but it's best to report it from that position right here. So if we add in 84.29 and 53.13, we get 137.4, but the actual angle of that is going to be the complement. So if we're going to report it as a vector, we want to say that it's 12.06 meters per second, but it's going to be up in that quadrant, and it's going to be equal to 42.58 degrees. Hopefully you'll be convinced of that. Now the VB2 is going to be just what we found, the 12.40 meters per second, but it's going to be coming down in that quadrant right there at the 53.13, which is the 345 triangle angle. So hopefully that's a complete problem. I didn't calculate in my example the efficiency, but we totally could find what the efficiencies were going to be right there. And I have tons and tons of extra paper here that from other examples and stuff, but these are the main ones for the concepts that we want you to be able to handle. So there you go, and class starts in 10 minutes. Wow, I didn't finish a lot of things today. I meant to. Oh well.